So problem 12 is what we call a banked curve problem. Okay, so I have this car that's driving around a curve, and what they've done is they've taken the ground and they've lifted it up here, right? Have it on an angle. Okay, this is called banking the curve. And we're doing this for reasons. It's going to help the car to make the turn so that he doesn't need as much friction between his tires and the road in order to make the turn. So here we go. Let's go ahead and run through. Again, I'm going to go ahead and do this on separate paper just because I'm that way. I like to have lots of space to do my work. On the actual AP exam, by the way, you would have more space. They really spread it out and give you plenty of room to do your work. It says the highway curve has a radius of curvature of 100 meters. It's banked at an angle of 15 degrees as shown above. Determine the vehicle speed for which this curve is appropriate if there is no friction between the road and the tires. In other words, I want to know what speed could I go around this curve where I don't need any friction to make the turn. Okay, we call that the design speed for the curve. Okay, so we're going to try to find that design speed, the speed where you don't need any friction at all. So I'm going to start by doing a force diagram. All right, so here we go. So what I'm going to say, hey, here is that car on that incline, right? I'm going to say ranged forces. There's a gravitational force going straight down, mg. Contact forces, the only thing touching the car is the road surface. Is he being pressed into that surface? Yes, he is. There's a normal force going perpendicular out from that surface. I didn't do a great job making that perpendicular exactly. That's okay. And they say contact forces, once you have a normal force, you say, well, there could be a friction if you're trying to slide. And we might ask, am I trying to slide downhill or uphill? But you know what? Since they said we want there to be no friction, not going to put it on. Well, that's it. That's the only thing touching it. There's no ropes, no wires, nothing else touching. That's it. That's our force diagram. You're like, well, okay, I need him to go around the curve. So our next step here is to do coordinate axes. And we remember that we always want to do first axis goes along the direction of motion. If this was like a rear view, then the motion would be, which is the way I usually do circular motion problems, the rear view is going to be going away from me into the page. So we're looking along the tangential axis here. All right. Now the other axes you want to use are going to be at right angles to it. You're like, well, how should we make these other axes go? Well, we want to make use of the fact that we know something special. When something's going in a circle, we know something special about the radial axis. We know along the direction toward the center of the circle that our acceleration is going to be v squared over r and directed inward. So we want to make use of that knowledge. So we're going to choose an axis that goes along the radius of the circle, a radial axis. So you say, well, where is the center of the circle? Well, this car is not going down into the ground and up around. We're not going in a circle like this. We're going in a horizontal circle around here. Do you see what I'm saying? So the center of the circle is straight left, not downhill. Straight left is the center of the circle as you drive around. So I want, and I don't usually like drawing axes on top of my picture, but I just want to point out that the center of the circle is over this away. Okay? So I'm going to have an axis going, this is my radial axis. And then up and down here is my z-axis, right? You know, and then tangential to the path, right along the path, tangential is in and out of the page. Okay, so that's it. So what force has to get split into components? I don't need to split the gravitational force into components. It's going along the z-axis. But I am going to need to split up that normal force. And you say, okay, I'm going to break it into radial and z components. So my radial component, going inward, right? You say, aha. And z going up, tick, 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 right? Okay, so this chain of arrows replaces that arrow. This angle of the incline here, I'm going to call it theta for right now. I know it's 15 degrees in this problem. That's going to be this upward angle here. So this side's the side that's adjacent. N is the hypotenuse, so this is n cosine theta. And then this part here is opposite. So that's going to be n sine theta. And you say, hey, this part is pointing toward the center of the circle. This is the force that is going to be centripetal that's going to make the driver turn. That's the reason why we're banking this curve. Because now I have a force to push me toward the center. I don't need any friction with the ground at all. If I go at just the right speed, this will be helping out, helping me to make the turn, which is important. It's going to make it easier to turn. You don't need as much friction, so it's safer for drivers when that curve is banked like this. All right. Plus, there's also the benefits that rainwater will tend to pour off. Go downhill, right? Flow downhill, and there's other nice benefits to having it banked. Okay, so there we go. So now what do we do? Well, you say we are trying to find the speed for which it's appropriate. You're like, well, the way we're going to do that, because they don't give us any kinematics information here, right? So we're not going to use kinematics. You say we're going to do sum of the forces in the radial axis. The sum of the forces in the radial axis. And we know that's equal to mass times that acceleration in the radial axis. My acceleration in the radial, we know that's got to be inward. It's what we call centripetal. And so I can substitute in the centripetal acceleration formula, speed squared over the radius. You're like, hey, there's that speed. That's what we're trying to solve for. You say, okay, my force in the radial, that's just n sine theta. So I've got n sine theta is mv squared over r. In this problem, do I know theta? Yes, I know it's 15 degrees. Do I know the mass of the car? Son of a gun, I don't. Do I know speed? That's what I'm trying to find. Do I know the radius? Yes, it's 100 meters. So like, okay, I've got two unknowns in this equation. I'm trying to find the speed where this force is exactly what I need to make me turn. But this force has got this n that I don't know in it. You're like, nuts. I need another equation that has n in it so I can get rid of this. Where am I going to get another equation with n? Well, from the other axis, of course. Let's do the sum of the forces in the z-axis. So if I do the sum of the forces in the z-axis, mass times acceleration in the z, Newton's second law, most important formula in physics, and you say, hey, my acceleration in the z, that's going to be 0. We're not accelerating up and down. We're just kind of going around in a circle like this, right? Right? Okay, we're not going up and down at all. And so the acceleration in the y is z. So you say, oh, and z is acceleration in the z is 0. And say, okay, well then let's write this expression. I'm choosing to call upward positive, and so I'm going to write this as forces up minus forces down. So I will have n cosine theta minus mg, right, equals 0. You say, okay, look, I know theta, I don't know m, right? I know g, so I've got two unknowns, n and m. Hey, look, I got two unknowns here. Wait, I forgot. I don't know m. I got m and n there, but you see m and n there. Something wonderful is going to happen. Rearranging this, let's get rid of n. Yeah, sure. And I'll say that n, when I rearrange this mess, I will get that it's equal to mg over cosine theta. That's an m. Okay. Whoop. Why not? What? Yeah, sure, why not? Okay, over cosine theta. And then I can go ahead, I can take this and substitute this thing in for n there. When I do that, something wonderful happens. Mg over cosine theta, it goes in place for n. Then I've got sine theta equals mv squared over r. And you say, hey, look at that. What's in both terms? I say, yeah, there's an m in both terms. So I can go, divide both sides by m. I'm trying to find that speed. Let's just move the r over there. And now I'm going to have g. Hey, by the way, what's sine over cosine? And it's just going to be tan theta. And then I have that r that I moved over. Sure, why not? And you say, hey, that's going to be, and I take a square root, and that's going to be v. Ta-da! Okay, now do I know values? Yes, I know 9.8, 15 degrees, and a radius of 100 meters. I can solve. And again, yeah, let's just run this out. 9.8, tan 15, and then that is under the radical. And the radius of 100 meters equals v. Plug and chug in my calculator. By the way, in case you're wondering, tangent of 15, let's not even worry about that, times 9.8 times 100, take a square root of that answer, and I get 16.2. So 16.2 meters per second is the design speed. That's the speed for which you don't need any friction to make the turn. This little component of the normal force is exactly what you need to turn. Okay, so that is part A. You say, gosh, that was a lot of work to go through for the first part of that problem. I hope the rest isn't so bad. Let's go move on. Here we go. Hey, the next part. They say, okay, on a dry day, when there is friction, right? Okay, that's why there wasn't friction here. It must have been icy or something. An automobile successfully negotiates the curve at this speed. You say, wait a minute, 25 meters per second. How does that compare? You say, well, that's faster than the design speed. So we're going faster than designed. Okay, so I'm definitely going to need some friction to hold me on the road. On the diagram below, in which the block represents the automobile, draw and label all the forces on the automobile. You say, okay, well, how is this going to be different? Well, this diagram is going to look just like the last one, except now we have friction. So which way is this car going to attempt to slide, right? You say, well, I'll still have a gravitational force. I'll still have a normal force, right? It's going to look the same, except now I'm going to have friction. If I am going faster than the design speed, then if you think about it, like here is that turn that you're making. Here's like a top-down view, right? I'm, I guess in the picture, technically it's coming out of the page towards you, whatever. So if it's coming towards us here, right? Then you say, hey, what would happen if there wasn't enough friction, if for whatever reason the car's going too fast, there's not enough friction, then the car would want to keep going straight, wouldn't it? And so it would go to the outside, to the uphill part. It would tend to slide out of the circle this way. It's going to tend to slide uphill. Do you see that? And so if it's going to tend to slide uphill, then the friction force must be opposing the slide. The friction is going to go downhill. Okay, if you're going faster than design conditions, I need to add in a friction force going downhill. I'm going to draw this over again here just so that I have my force diagram on the page I'm going to be working at. Let's see here. So if I did this, gravitational force, normal force, and then I'm going to have a frictional force now going downhill. I'm going to tend to slide uphill, so this friction force is going to push downhill. Right? I'm going to split this into components. Again, radial, and z, right? This is the theta there. This is n cosine theta, n sine theta, just like before. But now let's talk about this friction force. Hey, that friction force, is it going along one of our coordinate axes? And you say, no. The radial is straight to the left. This is going at an angle. So I'm going to have to split it up into components, right? So I'm going to split it up into components like so. Radial and z, left and down. Hey, you know that angle of the incline? It's going to be this one, right? That's the skinny angle, fat angle, right? Skinny, fat. Anyway, so here we go. So this got to be theta. So this side then would be the hypotenuse, that static friction times the cosine of theta. And this would be that static friction times the sine of theta. And that's my force diagram, okay, for traveling faster than the design speed. Hey, if you traveled slower than the design speed, too slow, you would tend, then this normal force here would be bigger than we need to turn, right? If we go slower, we don't need as much force. And this is too big, and so it's going to tend to push me, and then I would end up sliding downhill. And so then the friction would have to go uphill to hold me there. If you go slower than design speed, the friction force is going to go the other way, uphill. Okay, good enough. Hey, there we go. What are we doing from here? Well, now they'd like, that's the force diagram. We've drawn and labeled all the forces, so we're good. Now we want to find the minimum value of the coefficient of friction needed to keep them from sliding as it goes around the curve at this speed. Okay, specifically, this is going with this, because you see how this is above the B? So this is like the heading, the stem there, saying a curve at the speed of 25. That applies to everything here. Okay, when you indent, it's like kind of under that title. So we still have that speed here. Okay, so we're going faster, so we need that coefficient of friction that we need. So let's do it. Now, how is this going to change? I'm going to do the same thing. I'm going to set my sum of the forces radial and in the z. I'm going to put this in. It's just now I'm going to have that friction force involved too. It's going to be in both axes, isn't it? Okay, so let's go ahead and really quickly, I'm just going to whip through this. I'm going to try to pick up the pace here. Hey, we're going to do the sum of the forces in the radial axis is mass times acceleration in the radial axis, which we know is the centripetal. You say my forces in the radial, I didn't give myself enough space there. That was dumb. Inward is to the left. So that's going to be positive. So I'm going to have that n sine theta that I had before, but now I'm also going to have that friction cosine theta. Okay, that's going to be equal to mv squared over r, right? All right, putting that centrifugal acceleration in there for the acceleration in the radial axis. When I go to do the z-axis, on the other hand, sum of the forces in the z, mass times acceleration in the z. We've already talked about how this thing is not changing speeds up and down. The speed up and down is going to remain 0. So the acceleration up and down is 0. And I'm going to have now, I'll have this force going up, n cosine theta, and this force going down, and friction and gravity going down. So I'm going to have n cosine theta, right, minus mg, and minus this part of friction, right, minus that static friction times the sine of theta, okay? And this is, of course, going to equal 0. All right, take a look at this. I am trying to solve for the value of the coefficient of friction needed for this to make the turn, the smallest mu I can get away with. So it's the smallest mu I can get away with, right? The minimum coefficient, which means I need that friction force to be at its limit, right? So we're barely able to hold on to the smallest mu I can get away with. So that full static friction is working. And so that allows me to say, if the static friction is at its max value, then I can substitute in the static friction being, because just the max value is equal to mu Sn. Okay, I'm going to substitute it there, and I'm going to substitute it here. All right, because we're trying to find that mu, so I need to get that mu in the equation, right? So when I do that, here we go, n sine theta plus, and now I'm going to substitute in mu n, right? That's static mu times the normal force times the cosine theta, okay, is going to equal mv squared over r. Okay, going to the other axis, I'm going to have n cosine theta. Do you mind me doing both axes at once here? Hope not. And then where it says friction there, I'm going to be putting in mu n times the sine of theta. And this is equal to 0. All right, there we go. Okay, so we got the variable that we're interested in, right? We've got that that mu, okay, and actually we have it twice, once in each axis here. You say, okay, now do I know the rest of this stuff so I can solve for mu? You say, well, they didn't tell me n. I'm like, uh-oh, look at that. N shows up there, and there, and there, and there. You're like, huh. Do I know theta? Well, I know that's 15 degrees. Okay, good. Do I know theta, 15 degrees? Do I know the mass of the car? No. Do I know the radius of the turn? Yes. Do I know the speed we're traveling at? Yeah, we're 25 meters per second. We know that. So you're like, okay, so I'm trying to find mu, but I have n and m. What about over here? M I don't know. G I do know. Theta I know. Okay, so I've got mu, but I have two unknowns, m and n. So I have the same two unknowns in both equations, plus the variable mu. I'm going to have to do some substituting, rearranging and subbing around, and life will be good, I hope. Okay, so what I'm going to do is I'm going to go ahead and pick one of these, okay, this one, and I'm going to isolate the n, and then I'll substitute it in for n here and see what that does for me, okay? So I'm going to rearrange this guy. So I'm going to factor let me move this mg term to the other side, and then I can factor an n out of what's left. So what that's going to look like, I'm going to stop color coding now. I'm going to factor the n out. So it'll be n times cosine theta minus mu sine theta. And this mg I moved to the other side. Okay, I added that over. Okay, so now n, I would just take this bit in parentheses and put it underneath. So that normal force is going to be mg over the cosine of theta minus mu sine theta. Okay, and that coefficient of friction, of course, what I'm trying to solve, but I'm going to take this mess, and I'm going to substitute it in the other equation where I see n. That would be there and there. All right. So what does that look like? You're like, all right, mg over, yes, so here we go. Mg over cosine theta minus mu sine theta, right? Then times a sine theta. Okay, and now I have plus, I don't know, mu, I thought I wasn't going to color code anymore. Oh well, plus mu s and then times n. And so that's going to be another mg over cosine theta minus mu sine theta, right? And then times a cosine theta. Okay, and this is going to equal on the other side mv squared over r. Ta-da! Okay. Whew. At this point, you say, now wait a minute. Okay, I just got rid of the n. I eliminated the n by substitution. You say, but I had another, I'm trying to find mu, but I had another unknown here running around, and that's mass. But look, something wonderful just happened. There's an m in this term, an m in this term, and an m in this term. So if I divide through by mass, all the masses drop. There's an m in every term. Okay, so what I can do is I also notice now these two terms on this side, they have the same denominator. So I could make my life easier by combining those terms. So I'm going to have g sine theta plus, oh, I thought I'd make my life easier. Uh-oh. Mu, g cosine theta. Oh, that's ugly. Over that common denominator of cosine theta minus mu sine theta. Equals v squared over r. Okay. At this point, I know the value of everything in this equation except mu, right? Which pops up twice there. I lost my little subscript s. What can I say? Okay, anyway, so I just need to rearrange. I need to get that mu by itself. Okay, so I'm going to probably take this denominator, multiply both sides of the denominator, bring that over here, and then I can combine like terms. I am running out of space. That makes me sad. Like I said, they give you plenty of space on the actual AP exam. Am I going to jam it in this corner? You're like, I know Mr. C is going to jam in the corner. That's the sort of thing he does. No, I'm going to be nice. I'm going to go ahead. I'm going to go to another page. Holy cow. Right? This was a long problem. What I'm going to do is, yeah. Okay. Like I said, let me take this denominator, multiply it over here. Yuck. G sine theta plus mu g cosine theta equals, I'm going to distribute that v squared over r. Am I really going to do that? Yes, I am. I'm going to v squared over r times cosine theta minus mu v squared over r sine theta. Okay? Again, just a reminder, the variable we are trying to isolate is mu s, that static coefficient of friction. So I'm going to move this term to the other side. I'm going to move this term to this side. So I'll have all my mu terms collected on one side, all my non-mu terms on the other side. And then I'm going to factor out what's multiplying. So when I move this over to become positive, so I'm going to have mu s times g cosine theta. Move it over, it's going to become positive. So I'll have plus v squared over r sine theta. Over here, I've got this v squared over r cosine theta. And then I would have moved this g sine theta to the other side, so I subtract it over. And now, to get the mu by itself, this whole bit in parentheses, now I can just divide through. So my mu, at last, is going to be v squared over r times the cosine of theta minus g sine of theta all over this bit that was in parentheses there, g cosine theta plus v squared over r sine theta. Ta-da! Right? Whew! Holy cow, that is not a pretty equation. Okay, and you say, hey, we know the value of v, 25 meters per second. We know r, 100 meters. We know theta 15 degrees. We know G 9.8. We know theta 15 degrees. G, theta, V, R, theta. Yes, we know everything there. We can solve for that mu. Let's hope it comes out to be a reasonable value. That would be swell. So this is going to be 25 squared over 100 times the cosine of 15 minus 9.8 times the sine of 15 all over 9.8 cosine 15 plus 25 squared over 100 times the sine of 15. There we go. Okay, time for the calculator. Let's see here, 25 squared divided by 100 times the cosine of 15 minus 9.8 times the sine of 15. Okay, that's my numerator. Looks like it's just about on the nose, 3.5. I'm going to divide it by the denominator, which is going to be 9.8 cosine 15 plus 25 squared divided by 100 times the sine of 15. Close the parentheses in the denominator. Bam! We get a value of mu that we need to have at least, this is my minimum mu, of 0.3158. I'm just going to round that to 0.32. Okay, so that is our minimum mu that we need to make that curve. Okay, in reality, is that a very large mu? You say no. I mean, especially if that road is asphalt, the tires are rubber, no problem, right? I can have my road be damp even, right? And I'll still have a mu that good. If it's icy, I don't know. That's not going to be good enough, right? If it was covered with ice, and that's why you need to slow down. 25 meters per second will not work with that mu. Okay, and that is it. If the mu is smaller than that. So that's it. Okay. Yep, that's it for problem 12. Again, a problem like this on the AP exam, you typically free responses are worth 15 points, and you get 15 minutes for them is the way they used to do this. And so you'd say, hey, did we take 15 minutes? They try to make it so like each minute is worth a point. And you say, I don't know how long this took. I suspect it was longer than 15 minutes, though, but that's because I was stopping and explaining things, and it would be fine if I was just cranking it out myself. Okay, and that's the problem.